is we're going to go over the problem that is going to be covered on the assessment. So like I mentioned before, this is the scenario that we're going to be dealing with. We're going to have a ball that's going down a ramp. It's going to be traveling horizontally with no friction and no air resistance. And then when it reaches the end, it's going to compress the spring, and then it's going to launch the ball back, and then it's going to repeat. So the problem that we're going to have on the assessment is going to only deal with half of this animation. So it's going to start at the top, it's going to slide across the bottom, and then it's going to fully compress the spring. So there's going to be 3 different states that we're going to be dealing with. And we're going to start with state 1. So how we break this down, well, first off, the things that we're going to try to find in these problems are going to be the velocity at state 2 and the amount of compression that the spring experiences. So at state 1, we're going to have to figure out what type of energy is present. So there are 3 questions that we ask when we're trying to figure out what type of energy is present at each given state. So the very first question is there a height from the ground? So I look at the object, this is the thing that's moving, and we have to determine, is there a height from that object to the ground? So what we're going to do, I'm going to draw a line like this. So that's the height of the object, and obviously there is a height from the ground. This is going to be the height. Cool. So is there a height from the ground? Yes, there is. So this question number 1, is dealing with gravitational. So there is gravitational. And let me actually move this over here just for the sake of consistency with the other videos. It's not a U. So, gravitational potential, that's a check. There is a height from the ground at state 1. So at the state where it's at the maximum height, or it's at the very top of the ramp, there is a height from the ground. And just as a reminder, this is the ground. The second question is saying, does the object have a velocity? So this is dealing with kinetic energy. This is going to help us determine, is there kinetic energy present? So at the very beginning of the problem, we've released the ball and it doesn't have enough time yet to start speeding up. So we're going to say that the initial velocity when we start is going to be 0. So is there a velocity, or does the object have a velocity? No, it does not. So this means that there is no kinetic energy at state 1. And then lastly, at state, or the third question is there a spring that's being compressed or stretched at state 1? This is dealing with U elastic. And as you can see, the spring is not being compressed or stretched. So no, there is no elastic energy present at state 1. Is there any confusion about that? So state 1, we have gravitational potential energy. Any questions so far? Alrighty. So at state 2, that's going to be the point where it's traveling horizontally across the ground. So we're at state 1 there, and then state 2 happens right there, and then it slides horizontally. Now I know it's a ball, and we're going to assume that it's just sliding and it's not rolling. Okay, I want to make that clear. So state 2 is right here. So we ask ourselves those 3 questions again. So we have U grav, we have kinetic, and we have U elastic. And depending on how we answer these questions, that'll tell us what type of energy is present. So, is there a height from the ground at state 2? The ball is sitting there on the ground, so it is not above or below the ground. There's not a distance between the object and the ground. Let me get Jade for attendance. I got you. All right, and just make sure. Cool. All right, switch back over here. All right, so if there's no height from the ground, then there is no gravitational potential energy. When it reaches the bottom of the ramp, does the object have a velocity? Let's see. So when it reaches the very bottom, so right about here. So here, if I had a, I don't know if I can do this in Adobe Animate. I'll see if I can add a velocity vector, which will grow and shrink depending on how fast it's going. But right here, if I hit play, then obviously the object is going to move, right? Because it's reached the bottom of the ramp, right? So we do have a velocity at state 2. And at state 2, is the spring being compressed or stretched? No, it is not. So the only type of energy that is at state 2 is going to be kinetic. So at state 1, it was gravitational. And let me be consistent with the colors. So gravitational, we have kinetic, and by process of elimination, you can probably assume that at state 3, we'll have U elastic. So let's just double check. At state 3, this is the point where it's reached the maximum compression of the spring, and it's getting ready to launch it back up in this direction. So it's no longer traveling, so it comes down, it travels to the right, and then the instant right before it switches direction and starts to move this way, my velocity is 0 because it was initially going to the right, but then it switches direction and goes to the left. And anytime when you switch directions, your velocity has to go, like we'll call this way going positive. So anytime that I go from positive to negative, it has to cross that 0, that horizontal axis. So if this was my velocity versus time graph, I would slow down, I would hit 0, and then I would be traveling backwards. Okay. So this is the instant right where it's crossing the horizontal axis, where my velocity is 0. So I'm going to go back in here. So this is going to be U grav, kinetic, and U elastic. I should have written that before class to save some time. All right, so at state 3, is there a distance or a height from the object to the ground? Again, remember this line down here is the ground. And the object is sliding across the ground, so there is no distance between them. So no, there is no gravitational. This is the point where it has reached its maximum displacement. So its velocity is 0, so there is no velocity. And we know that the spring, if I look back, this is what the spring looked like before, and it is obviously compressed here. So yes, there is a spring that is being compressed or stretched. So that means that we have U elastic at state 3. Make sense? Okay. So now what we're going to do is we're going to write out our conservation of energy equation. When you're doing this for the assessment, all you'll need to know is the equations that you'll see after, like when we go through the video. I'm going to box the actual equations so you don't have to go through this whole process on the assessment. But I'm going to go through this so you guys understand where these equations are coming from, so you can understand how this all works. But when it comes to the assessment, all you need to know is the final equations and just plug in. Cool? All right. So, what we're given is this information here. I'm given a mass of 15 kilograms. I'm given the acceleration due to gravity in my class, just to keep the math simple, is going to be 10 meters per second squared. The height that the object is at when it starts, so this h right here, is going to be 60 meters above the ground. And then this is the spring constant, which is telling me how stiff or how springy that spring is. That's just the characteristic of the spring. So that's going to have a value of 400 newtons per meter. And all the spring constant means is if I was to stretch the spring the distance of 1 meter from its original length, if I stretch it a distance of an additional meter, that particular spring that we're dealing with is going to be requiring 400 newtons in order to stretch it 1 meter. That's all the spring constant is. So my objective is I want to figure out the velocity at state 2, and I also want to know how much does the spring compress at state 3. Make sense? All right. So these are the equations that I wrote down. These are the final equations, but I'm going to show you how I got these. Okay? All right. So we have mass, we have gravity, we have height, and we have the spring constant. So let's figure out. So the conservation of energy states that all the energy that I start with must equal the amount of energy that I finish with, assuming that we're in an ideal situation where there's no friction, there's no air resistance, and nothing is lost to the environment. All the energy is conserved. So the way that we do this, the way that we represent it, is the energy total at state 1 must equal the total energy at state 2, which will equal the total energy at state 3. So throughout this entire process of sliding, like going through this whole animation, the total amount of energy remains constant. Nothing is lost. So the energy at state 1 was what? We had gravitational, right? So state 1, we had gravitational potential. So that's what I'm going to write down here. So I'm going to have U grav, and this is going to be state 1. That's what this little subscript represents. So state 1, state 2, and state 3. So the energy at state 2 was kinetic energy. So I'm going to write kinetic. And then lastly, it was U elastic. Cool. Any questions so far? Okay. Sorry, just double checking the chat. Now, what I'm going to do is I'm going to write in what these formulas are. So I'm going to write down what gravitational potential is. I'm going to write down what kinetic energy is. And I'm going to write down what elastic energy is. Elastic potential, sorry. So the equation for gravitational potential is just going to be the mass times the acceleration due to gravity times the height of the object. Kinetic energy is going to be 1/2 times the mass times the velocity squared. And then U elastic is going to be 1/2 times the spring constant times the amount that spring is being compressed or stretched squared. And then I'm going to put parentheses over here with the kinetic one just to be consistent. All right. So this right here is my conservation of energy equation. So all it's stating is the amount of energy that I start with at state 1 is going to equal the amount of energy at state 2, which will then equal the amount of energy at state 3. Now, there's only one of these that I can actually solve for to get a number. If I look at my knowns, I have mass, gravity, height, and my spring constant. So which one of these would I be able to put the numbers in and solve for and get a number? It'd be this one here. I have the mass, I have acceleration due to gravity, and I do have the height. So I could actually get a number, not a hashtag. I can actually get a value for my gravitational potential energy. Once I get that number, I can then set it equal to either this one or that one, and then I can solve for either one of those variables, because I need to solve for the velocity at state 2, and I also need to solve for how much the spring is being compressed. Now, we can't do that in the same go, so there's going to be two different steps on how to do it. And again, that's why I've got two different equations here. So let's start off trying to solve for my velocity at state 2. Copy that. Oops. Copy, not paste. So solve for the velocity at state 2. So that's what we're going to be doing right now. Paste. So I have my state 1 energy, which is gravitational, and my state 2 energy, which is kinetic, and I'm solving for my velocity. And what I'm going to do is, instead of having a box, I'm just going to change the color. So I want to get the red variable all by itself. So in order to do that, I have to do a little bit of algebra, and it's not hard. So what I'm going to do is, in order to get rid of this 1/2, I have to multiply by 2. 2 times 1/2 just goes to 1. So it cancels out over here. And then if I did it on the left side or on the right side, I must do it on the left side. So this part is gone. Now I just have m times v squared. If I want to get rid of the m, because it's multiplied by v squared, I divide it, so the m's cancel there. I divide by m over here. And since I've got an m for mass and an m down here for mass, it also cancels on the left side. And if I'm going a little too fast, that's why I'm recording this on YouTube, so you can go back and rewatch it. So this is what I've currently got. And then switch back to red. Velocity. So I've got 2 times the acceleration due to gravity times the height, and then I have v squared. So in order to get rid of a square, I have to square root, and this square root will cancel with this 2. And since I square rooted on the right side, I must do it on the left side. So the equation that I get for my velocity, now this is the velocity at state 2, is going to be 2 times the acceleration due to gravity times the height, all under the square root. So if I'm given the mass, the acceleration due to gravity, the height of the object, and the spring constant for this problem, for this one here, and I'm asked to solve for the velocity at state 2, this is the equation that you need. I've already done the algebra, and if you write this down on your formula sheet, you don't need to do any of the stuff that I just did. You just need this equation, plug the numbers in, and then you get your answer. I'm basically handing you the assessment. Okay? So that's solving for my velocity at state 2. So we're halfway done. Halfway there. All right. And I hope I don't get a copyright strike for that. All right. And variables I keep in square brackets. All right. So in order to solve for the amount that the spring is being compressed or stretched, if I go back up here to my conservation of energy equation, this is the equation here that has delta x in it. Now, I cannot use this equaling to this and then getting a number, or like doing what we just did, because we don't know the velocity. It wasn't given to us. But because all of these three states are equal to each other, we're going to do state 1 equals state 3. And the thing that we just did before was state 1 equals state 2. But it doesn't matter because they're all equal to each other. So we're going to do state 1 equals state 3 when we're solving for this. So state 1 equals state 3. The energy that's at state 1 is going to be the mass, and I'm going to stay consistent, mass times acceleration due to gravity times the height. That's equal to 1/2 times the spring constant times delta x squared. Now, I want to emphasize that this delta x is not saying my change in x position. What it's representing is my displacement. This is the common variable referring to displacement. So it's not correlating to any kind of axis. Sometimes, like when we start talking about the Hooke's law, when we talk about how much spring force something has, the delta x can be represented in the y-axis too, but all it represents is just the displacement of the spring. That's just a little side note. Okay, so the variable that I'm solving for is this delta x. So if you look at this, and I slide over here and I look at this one, it should look pretty similar, right? I've got mgh over here. I've got 1/2 mv squared over there. Looks pretty close, right? Just the variables are a little bit different. So we're going to do the same kind of process. I need to get delta x by itself. So I've got 1/2. Now I want to get rid of that. So I multiply by 2. It cancels over here. Multiply by 2. I divide by my spring constant. So it will cancel on this side. Divide by my spring constant over here. And I'm going to rewrite all of this. It's a little bit cleaner. So I have 2 times the mass times acceleration due to gravity times the height all over my spring constant, and that equals my delta x squared. In order to get rid of the square, I square root. Cross that out. So what I'm left with for the equation is going to be delta x equals all under the square root. Cool. So, this is the other equation that I would highly recommend you write down. I've done all the algebra for you. You don't need to do the algebra. Now, this is where people have been running into issues. How do I plug this stuff in? And how do I make sure that the order of operations is proper? So because I've got a fraction inside of a radical, or inside the square root, when you plug this into a calculator, sometimes people will plug this in, and this is actually what they're calculating. So they're only calculating that, and that is not the same as what I've got up there. The difference is that the square root only covered the numerator when they plugged it in, but what they need to do is actually include the top and the bottom. Okay, so what I'm going to do now is I'm going to show you a kind of foolproof way on how to do this on Desmos. Okay, so maximize this projector. All right, switch over here. So on Desmos, desmos.com, desmos.com, what I can do is I can let us start off with finding the velocity. Okay. So what I'm going to do is I'm going to make sure that inside of Desmos, I'm going to have this equation, this one here, the square root of 2 times g times h. I'll make sure that looks exactly the same as in Desmos. Okay? So here's a way to do it. And if you do it this way, it's foolproof. There's absolutely no way you can get this answer wrong if you do it the way that I'm getting ready to show you. So, I start off with my square root. So the square root of 2 times, and watch this, I put the letter G times, and then the letter H. Whoops, lowercase. Now the case doesn't really matter, but I wanted to make sure that it looks exactly the same as this here. So as you can see, I have the radical, and underneath the radical I've got 2 times G times H. And the 2 times G times H is inside of the radical. Now, does that match with what I've got currently? Yes. Now, here's something that's super useful. Notice here it says add slider. So if I hit all, what this is doing is it's plugging in 1 for G and 1 for H. Now what we can do is instead of having 1 and 1, I can actually plug in the values of my knowns. So in this case, what I can do is for G, I don't want 1. Luckily, they've already got 10 right there. So I know that the value for G in my problem that I give you from Mr. Applewhite's class, the value for G is 10. For the height, notice I don't have a 15. It goes down to -10 to +10. And the value for my height in this case is 60. So how can I change that? If I switch back over here, this is my max, this is my min. So if I click here, all I have to do is type in 60, and I click off of it, and I move my slider all the way to 60, and what Desmos is doing is it's taking H equals 60, plugging it in for H, taking 10, plugging it in for G, and then calculating the value. So 34.64. Now, when I give you guys a problem like this, I will tell you how many decimal points I want you to round to. I don't want to confuse you guys with significant figures or any of that kind of stuff. I will explicitly ask, round to the nearest whole number, 1 decimal, 2 decimals. For the height, I'll say to the nearest 1 decimal point. So I've got 34.64. So 34.64. So let's just round to 1 decimal point. Alberta, let me get you for attendance. Thank you for letting me know that you're here. Maximize that. All right, so if I'm rounding to 1 decimal point, I want this to be a little bit of a reminder, or kind of a review. So if I'm rounding to 1 decimal point, that's this guy. This is the one that I'm looking to change. Do I go up by a factor or by a value of 1, or do I keep it the same? So if I'm rounding up, this 6 will become a 7, and if I round down, it'll remain a 6. And in order to determine whether I go up or I remain the same, is I look at the one that's immediately to the right, and if it's a 5 or above, 5 or higher, then I'm going to increase it by a value of 1. If it's 4 or lower, then I'm going to keep it as a 6. And this is a value of 4, so that means that I round down. So my final answer is going to be 34.6, and that's my velocity at state 2. And the velocity is going to be in units of meters over seconds. So that is the final answer for velocity at state 2. Now I know, again, this is probably a little long-winded, but on the assessment, this is where you start. I know this is my equation. I plug the numbers in into Desmos just like this, get the answer, and I round properly. That's it. Okay? Now, let's do the same thing, but with this equation. So, some people like to plug in the numbers, but I would definitely recommend doing it the way that I'm showing you in Desmos to make sure that the order of your variables is done properly. So let me show you how this is done. This one's a little bit less straightforward. So when it comes to Desmos, I'm not aware of a way to provide a fraction. So if I do 1 divided by 2, notice how it automatically puts it 1 over 2. But if I have 3 times 4 divided by 5, and I want it not to look like that, I want it to look like this. So 3 times 4 on top divided by 5. This is what I'm looking for. Aesthetically, this looks like what it should be on my paper, hypothetically. This does not look the same. Technically, these are mathematically correct, but in order to make sure that everything matches up, this is the process that you need to do. So, this is the equation. I have 2 times the mass times gravity times height over my spring constant. So, what I'm going to do is I'm going to do open parentheses, close parentheses, and this is going to contain everything that's in my numerator. So I'm going to have 2 times mass times gravity times height. Then I'm going to hit the right arrow to go behind that parentheses, hit divide, and then I'm going to put a lowercase k. Now, once I've gotten the shape of it looking right, so what I have just done is this. Whoops, I'm gonna do a different color. Is this part right here? So the 2 M G H and then the K. So I've gotten that set up. Now, the tricky part that some people get tripped up on is putting the radical. So what I would recommend is clicking on the front, putting the square root, and then selecting everything right here. And all right. So you're going to copy it, or you can cut it and then paste it inside of here. So the shortcut for that is I select everything over here, I hold down the control button, and then I hit the X key. So that's going to cut whatever's there. So I've now not just copied it, but I've removed it. And then what I'm going to do is I'm going to click inside of the radical. I'm going to hold control, and then I'm going to hit V to paste it. Okay? So this should look like this equation here. And once you have verified that it looks exactly the same, then you can start putting the values in for your variables. So when it says add slider, I'm going to add all. If I go back up, and look at my, excuse me, I'm going to look at my knowns. So the value for my mass is 15. So when I switch back over here, my mass variable, I'm going to switch this to 15. My gravity is going to be 10. My height was 60. I guess I can just plug that in. 10. This was 15. So that way you don't have to put in the sliders. And then 400 for my spring constant. So these are my knowns. So if I look back, my knowns are right here. So M is 15, G is 10, H is 60, and K is 400. And that should match what I've got over here. Now, if you do this properly, you're virtually guaranteed to get the answer correct. So all it's doing is taking these values, plugging it into this equation, and then getting a value. So what we end up getting is, I need to change the values. So in real life, this would be difficult to actually, the scenario with these numbers would be difficult to actually play out, because what this is telling us is that our amount of compression of the spring is, so delta X, how much the spring is being compressed, is a total of 6.708 meters. So that's a lot. That's a super long spring that's being compressed. So realistically, this wouldn't actually happen. I'm not going to get into that. So if I say round to the nearest 2 decimal points, I've got 2 decimal points after the 2 numbers after the decimal point. So here's the decimal point, and I've got 1, 2. So the one that I'm going to be modifying, or potentially modifying, is this value here. So again, since this is the one that I'm looking at, I look at the one that's immediately to the right, and if it's a 5 or above, I'm going to round up, and if it's a 4 or below, I'm going to round down. So the value is an 8, so I'm going to round up. So that makes my rounded answer 6.71 meters. That is the value for my delta X. And then let me just clarify. So round. round to 2 decimals. Cool. So that's my final answer for how much the spring has been compressed. Now, usually when we go through problems like this, I ask you guys to make sure that the answer that you get seems realistic. In this case, I pulled out random numbers. So this technically isn't realistic for the amount of compression of the spring. I will ensure that the answer that you should get on your assessment is realistic. But the process will be the exact same. Okay? So, just as a quick review, or a quick recap, we are given a problem where a ball starts at the top of a ramp. It is sliding with no friction, no air resistance. We're assuming that it's not rolling either. It's going to go down a ramp. It's going to slide across the ground, again with no friction, no air resistance. Then it's going to fully compress the spring, and then it's going to get launched back. So the animation that's being shown now is made to loop, but we're only going to take half this animation. So the point where we fully compress the spring is where we're going to stop. So what we did was we figured out what type of energy was at state 1, and it's going to be gravitational because it does not have a velocity at state 1, and the spring is not being compressed or stretched. State 2, it reached the bottom of the ramp. It's traveling across the ground, so there is no height. There is a velocity, and the spring is not being modified at all, so there's only kinetic energy present. At state 3, this is the point where the spring has been fully compressed, so my velocity is 0, there's no height from the ground, and there is the spring that's being compressed, so the only energy that's present is U-elastic, or elastic potential energy. Then, what we did was we looked at our knowns and our finds. We were asked to find the velocity at state 2 and the amount of compression of the spring. And in order to kind of give us a guide on how to figure those two variables out, those two variables, two unknowns, we use the conservation of energy equation. So the amount of energy at state 1 equals the amount of energy at state 2 equals the total amount of energy at state 3. And we use the information from those questions that we just asked to write down the energies at each state. So gravitational at state 1, kinetic at state 2, elastic at state 3. Then all I did was I substituted in what these were, what the formulas were for each one of these. And these equations you should have written down on your formula sheet. If not, I will also provide those fundamental equations. So U-grav equals this, and so on. Then we solved for the velocity equation, or the velocity unknown. And because I know that state 1 equals state 2, I set those two equal to each other. Because I have all the variables for state 1, I have mass, gravity, and the height. I set them equal to each other. I solved it algebraically. And again, you don't have to do any of this. All you need is this equation here. Now it's assuming if I give you these variables here, and like if this part looks like the assessment, then you're off to the races. You're good to go, which most likely will happen. So all I did was I plugged in the equation, or the values for gravity and the height into this equation, and then I got my value for velocity. And with this one I said round to 1 decimal. And we reviewed how to round properly. And then finally, this was state 1 and state 3, because we can't do state 2 and state 3 because I was not given the velocity. I need to find delta x, and I have everything here, so I set state 1 equal to state 3. State 1 equals state 3. I did some algebra. So this is the gravitational potential. This is the elastic potential. Did some algebra. Got my final equation of this. Again, this is another one that you should write down. And then I plugged it into Desmos. And when we were talking about Desmos, make sure that the equation that is inside of Desmos looks exactly the same as what's on your formula sheet. Make sure it looks exactly the same. And then instead of having to deal with the actual slider part, you could actually just plug in the values. So if instead I gave you mass is equal to 800, I just plug that in and then the problem automatically updates. But in this case it was 15. My gravity was 10. And let me show you. So gravity was 10 right there. Height was 60. I verify 10, 60, and then my spring constant was 400 right there. And it is 400 right there. Cool. All right, so are there any questions? Is everybody good? I know that was a lot of information, but I wanted to make sure that I had the animation in there and I had the figure, so the figure looked nice and neat. I wanted to redo what I covered a couple classes ago, just so it's a lot more concise. So does anybody have any other questions? All right. So I'm going to go ahead and end the live stream now. Where is my mouse?